Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on August 13th, 2025, which was released about 3 days ago. The big idea is a tiny add-on that learns to shape the starting noise for diffusion image models, recovering much of the quality gains of heavy test time optimization while keeping inference almost as fast as before. The paper is titled Noise Hypernetworks, Amortizing Test Time Compute in Diffusion Models. And as we will see later, the implications for deployment speed are quite significant. In short, a lightweight noise hypernetwork amortizes reward-guided optimization, avoiding per-sample gradients and preserving diversity. Building on that, tweets highlight reward hacking risks in direct fine-tuning and pitch noise hypernetworks as a principled fix, subsuming test time optimization into training, with modest engagement shown. Alright, this figure shows side-by-side grids comparing base generators to the same models with the noise hypernetwork applied, using the same starting noise. The top two rows are SANA Sprint, then SANA Sprint plus Hypernoise, followed by FLUX Schnell and FLUX Schnell plus Hypernoise. Building on our intro, notice sharper prompt alignment and cleaner composition, like clearer bridges, brighter lighthouses, and the smiling pizza with consistent pose, while style and diversity stay intact. Next, this schematic walks through training on the left and inference on the right. Focus on the full diagram. A LoRa-based noise network takes standard noise, adds a small residual, and produces optimized noise that feeds the frozen generator. The training loop maximizes a reward while adding KL regularization on the residual size. Moving to the right panel, inference becomes simple. Transform noise once, then run the base model to get higher reward images, keeping latency near original speed. Okay, this figure contrasts two training paths while optimizing a redness reward. The top row shows the noise hypernetwork gradually increasing redness but keeping structure and detail intact across training steps. The bottom row shows direct LoRa fine-tuning, which quickly saturates into flat red images, indicating drift from the base image manifold. Notice the arrow labeled Optimize Redness Reward, which marks progression over steps, and the clearer object fidelity in the top row compared to the collapsed visuals below. Now this plot quantifies that redness study. Focus on the whole chart first. The orange solid lines track redness reward, while the gray dashed lines track image reward score, both over training steps. Notice how direct LoRa fine-tuning pushes redness up quickly, but steadily drags image reward down. In contrast, the noise hypernetwork ramps redness to the same high level, yet keeps image reward nearly flat, showing little quality loss while meeting the target objective. Moving to the GenEval table, the key story is efficiency with gains. Focus on the full grid first. The rows list base models, then the same models, plus the noise hypernetwork, followed by heavy test time methods in gray for reference. The highlighted rows show consistent mean score bumps. For example, SD Turbo rising from 0.49 to 0.57, and SANA Sprint from 0.70 to 0.75, while inference time stays near 0.3 seconds rather than tens of seconds. Wrapping up, two takeaways stand out. First, a small noise hypernetwork learns to tilt the input noise toward higher reward images, preserving diversity while staying near base speed. Second, the method avoids reward hacking seen in direct fine-tuning by constraining changes in noise space. Thanks for listening. I am Alex, signing off.